Good evening, everybody. It's not rocket science. So why is rocket science considered to be so hard?
What do you do?
Well, I don't mean to boast, but I'm a brain surgeon.
Brain surgery? Not exactly rocket science.
And that's what I'm talking about, rocket science, not rocket technology, not rocket engineering. I'm not going to tell you how you can go about building your own Saturn V in your back garden. It's about how we use rockets to get around in the solar system. So I'm going to be talking about what rockets do. I'm going to be talking about orbits. I'm going to be talking about how we get from one orbit to another, for instance, how we get from Earth to Mars, and how we can use gravity assist to help us get around the solar system. And then I'll finish by looking at these mysterious parking places in the solar system called Lagrange points. So firstly, what do rockets actually do? Well, if you ask Joe Public, what's the primary function of a rocket, you'll often get the answer, well, it's to lift objects up above the atmosphere. Well, yeah, sort of, but not quite. For instance, the space station and the Hubble Space Telescope are actually in the Earth's atmosphere. It's rather thin up there at an altitude of 4 or 5 or 600 kilometers, but technically it's still part of the atmosphere. If you want to put an object into Earth orbit, what you need is not necessarily vertical height. What you need is horizontal speed. Yes, it's a good idea to reduce atmospheric drag as much as possible by getting as high as possible, but it's not strictly necessary. Newton understood this, so we've known about the need for horizontal velocity for more than 300 years. Newton said in his Principia, what if you were to put a cannon on top of a mountain and fire the cannon sideways, so you have a horizontal speed of the cannonball? If it's not going very fast, it'll fall to ground at position A, and if it's going faster, it'll go further, and so it'll hit the ground at B. And if you fire it fast enough, it'll go all the way around the Earth, as indicated by the dotted line C. So this idea of the need for horizontal speed was certainly understood by Newton. He also realized that if the Earth had a stronger gravitational pull, then you would need to fire the cannonball at a higher velocity. The stronger the gravity, the faster you need to go to stay in orbit. That's a central theme that I'll come back to time and again in this talk. So, rockets go up? Well, yeah, sort of. To start with, it certainly launches vertically. But if we watch the Saturn V, it's not long before it starts to tilt over because it needs to increase its horizontal speed. It's not the vertical speed that matters. And that's not a trick of perspective, that is a genuine tilt of the rocket. And to illustrate it, I've used a Saturn V rather than use some other rocket which might explode shortly after launch. If you don't have horizontal speed, then basically you go vertically up, and when you're done, you come vertically back down again. For instance, the Blue Origin New Shepard launch that took Captain Kirk into space some time ago basically didn't have any horizontal speed, so it just went straight up and came straight down again. It went up to an altitude of 100 kilometers or so, but came down and landed not so far away from where it was launched. So the horizontal speed is key to what we're talking about. So let's think about orbits and how things move. Well, an orbit is simply the path of an object affected by, strictly speaking, only gravity. In other words, if we've got a rocket out in space and the rocket engine is firing, then the path of the rocket is not an orbit because we only think about gravity affecting the motion of particles in an orbit. So a rocket will get you from one orbit to another. We're all used to the idea, I'm sure, of planets in orbit around the sun and moons in orbit around their planets. Kepler observed that the planets orbit in ellipses, and Newton figured out why that was by applying his law of universal gravitation. Newton found that the orbits of planets are ellipses or one of these other conic sections. If you take a cone and slice it horizontally, you get the slice of a circle. If you slice at a jaunty angle, you get an ellipse. If you slice at an angle that's parallel to one of the sides of the cone, you get a parabola. And if you take a larger angle slice, you get a hyperbola. 4 different curves. You can think of them, if you wish, as a circle just being a special case of an ellipse that's the same dimension in both directions, and a parabola is, if you like, an infinitely stretched ellipse. So you can think of them as belonging together, or you can think of them as being 4 separate shapes. If we plot them out here of orbits around the sun indicated by the yellow dot, we can see circles, ellipses, parabola and hyperbola. And it just so happens that these curves that describe orbits around the sun are also the same curves that define the shapes of mirrors that we can use in telescopes. Some telescopes, if we take a slice through the mirror, might give us the shape of a circle. Some telescopes will have elliptical mirrors, some parabolic, and some research telescopes or research grade telescopes will have hyperbolic shapes to the mirrors. And the reasons that orbits are the same shapes as the mirrors is because the maths is basically the same for both sets of equations. Now, planets follow essentially closed elliptical orbits, but if an object drops into the solar system from way out, for instance, way out in the Oort cloud, a long, long way, perhaps a light year or so away from the sun, and it starts with essentially 0 velocity and falls into the solar system, then it will follow a parabolic path, as indicated by one of the red lines here. If an object comes into the solar system not starting with 0 velocity, but if it actually enters the solar system with a finite velocity and travels through the solar system and out the other side, then it will follow a hyperbolic orbit. And we've seen this on a limited number of occasions. For instance, back in 2017, the object this rock came into the solar system in 2017 and followed the path of the white line there. So it was tracked once it was close enough to actually see it, and the path past the sun and its speed as it passed the sun told us that this must have had a finite velocity and hence must have came from outside the solar system, and indeed ultimately will leave the solar system at a similar speed once it finally makes its way out again. So we have a good understanding of elliptical and circular orbits and parabolic orbits of comets dropping in from the Oort cloud and hyperbolic orbits of objects passing through the solar system. If we think about the relationship between the distance from an object to the sun and how long it takes to go round the sun, the orbital period, here's a little cartoon that gives us an idea of what we're talking about. The green planet is closer to the sun, so the gravitational pull from the sun is stronger, and so the planet moves faster to stay in orbit, so it has a short year. Compared to the red planet, which is further away from the sun, so the gravitational pull from the sun is weaker, and so the planet moves more slowly to stay in orbit, so has a longer year. Let me just run that animation one more time. Notice that it's not simply a longer year because the red planet has further to go. It is moving more slowly in terms of kilometers per second because of the weaker gravitational pull of the sun. And this idea is important enough that I'll revisit this idea a little later. But we can see that this is a rather busy little animation, but we can see that when we look at objects orbiting close to the Earth or objects moving a little bit further away from the Earth. So in this animation, the space station and the Hubble Space Telescope are very close to the Earth, orbiting once in 90 minutes. GPS and Galileo satellites are taking 12 to 14 hours to go round the Earth. And further out still is the geostationary orbit, where an object will take 24 hours to go round the Earth and hence effectively hover above a particular point above the Earth's equator. And of course the planets know exactly how fast they should go. If we plot out how long it takes a planet to go round the sun on the vertical axis there, written in Earth years, and we plot that as a function of the horizontal axis, which is the distance of the planet from the Sun, in multiples of the distance from the Earth to the Sun, in other words, astronomical units, we can see that Newton worked out exactly what that relationship could be. But even before Newton worked that out, you can see that the planets know exactly how fast they should be moving at a given distance from the Sun. No surprise to find the solar system is nice and orderly, and all the objects going around the Sun lie on that straight line. If we think about what's happening with one object orbiting around another, strictly speaking, one object doesn't necessarily orbit the other. They orbit around their common centre of gravity. So for two equal mass objects, they would orbit around a point halfway between them. Whereas if the two objects were of different masses, as shown in the top right, then they will still orbit around their common centre of gravity or centre of mass, but you can see that the smaller object moves a greater distance. In other words, the centre of mass is closer to the larger object. And the bottom left, we see that is a little more extreme. Notice that the centre of mass, indicated by a small cross, actually lies within the larger object in this case. And if we take that to the extreme in the bottom right, it is possible that a small object like a planet can make a large object like a star wobble, because again they are both moving around their common centre of gravity. And that's how exoplanets can be detected. We might not be able to see the planet, but because the star is moving not around its centre but around the centre of mass, which is slightly off centre, the star is actually wobbling. So if we look at the spectrum of the star and look at its spectral lines, we can see some of those lines might be blue shifted if the star is moving towards us, or red shifted if the star is moving away from us. And so by looking at these small spectral shifts, we can see how much the star is wobbling, and hence we can infer the existence of exoplanets. A very important way that we have determined the existence of many thousands of planets beyond our own solar system. But it's rather embarrassing to have to admit, especially as I'm a physicist, that working out what's going on with two objects is easily soluble. But when it comes to working out what happens when we have three objects in motion, actually it's an analytically insoluble problem. We don't know how to solve the problem. We can write down the equations, but we can't work them out. We can get computers to tell us approximations to how bodies move, but we can't solve it with pen and paper as an analytical problem. So if we look at three objects moving around each other, in this simulation we can see at first it looks like they're very well behaved, three elliptical orbits. But if we watch them a bit more closely, we realise they're not actually ellipses. And if we follow this simulation, we can see that it doesn't take long before we end up what looks like a total spaghetti. So yes, we can simulate, we can calculate the forces involved. We know what the forces are. Newton told us that the gravitational force between two bodies depends only on the mass of those two bodies and the distance between them. So it's an easy calculation to do, but analytically there are very few systems we can set up that give us nice analytic solutions. So we have to rely on simulations like this. So how do we use our knowledge of orbits to get from one place to another in the solar system? Let's look at Mars and then think about other planets. So here's a little animation of how the InSight probe back in 2018 was sent from Earth to Mars. There's Earth at the bottom of the screen there, the little pink dot, and we are trying to get to Mars. And if you follow the launch of the InSight, we see that it's on its way to Mars. But by the time it arrives at Mars, the Earth has travelled more than halfway around the solar system. It takes about 8 months for a probe to get from Earth to Mars. Notice that as it approaches Mars, Mars is actually going a little bit faster than our probe. Let's just watch that again. After the probe leaves Earth, it gets closer to Mars. But as we get very close to Mars, notice that the probe is a little way ahead of Mars, and Mars is actually catching up the probe, which means the probe is moving more slowly than Mars when it arrives at the Mars orbit. And that matters in terms of what we need to do in terms of firing our rocket engines in order to make sure that when we arrive at Mars, we can rendezvous. So let's have a look at the so-called Hohmann transfer. That's a little bit complicated. Let's just dim that out and make life a little bit simpler for ourselves. Let's assume that Earth is in a circular orbit. We know there are ellipses, but let's not worry about that complication for the moment. There's Earth in orbit around the Sun, and there's Mars in orbit around the Sun. The most efficient way of getting from Earth to Mars is to leave Earth at one point, as indicated in this diagram, and arrive at Mars when Mars is opposite the Earth in terms of the other side of the Sun. You might think it would be more sensible to leave Earth and arrive at Mars when they're on the same side of the solar system. But no, when you actually look at the energetics and how much fuel you have to burn to get from A to B, it turns out to be more efficient to leave Earth when it's on this side of the solar system and arrive at Mars when it's just opposite on the other side of the Sun. The actual transfer orbit is called a Hohmann transfer. That's the blue line. Let's just take the green and the red away for just a moment. So the blue orbit, the Hohmann transfer, is actually an orbit around the Sun. Although we think of it as a transfer from one orbit to another, once we are in the Hohmann transfer, we are orbiting the Sun. And you notice that it's an elliptical orbit, and the ellipse, when it's closest to the Sun, just touches the Earth orbit, and the ellipse, when it's furthest away from the Sun, just touches the Mars orbit. And in order to get from the Earth orbit in green to the blue line, we have to go a little bit faster, because we can see that we are, in this case, we remember what the Earth is going anti-clockwise around the Sun. So in order to get on the blue line, we have to go a little bit faster. We have to give it a further nudge to the right. So if we want to leave Earth and get onto the Hohmann transfer, we have to fire our rockets and change the velocity of the spacecraft or the space probe. It's a so-called delta V, a change in velocity. So most rocket scientists talk about delta Vs. It's not really the acceleration that matters, it's how much you change your velocity by. And therefore everything is calculated in terms of delta V. So a Hohmann transfer, the first thing you need to do is to give your spacecraft a kick with your rocket engine in order to get out of Earth's orbit and onto the blue line. And remember what we saw in that previous animation? When we arrive at the Mars orbit, Mars is actually traveling faster than we are. So when we arrive at Mars orbit, if we want to catch up with Mars, we have to give it another delta V and accelerate in order to go at the same speed of Mars if we want to then go into orbit or land. If we decide not to land on Mars, what would happen? If we decided not to give it that second delta V, this extra kick up here, well, if we decide not to accelerate and go at the same speed of Mars, we would drop back along that blue orbit again. In other words, we would continue on the Hohmann transfer, and we would end up back at Earth orbit distance again. So at first sight, that might sound like a very good thing. If you decide to go to Mars, well, it'll take you quite a few months to travel on that blue line to get to Mars. But if you decide not to land on Mars, how do you get back? Well, if you simply do nothing, you'll end up coming back to Earth orbit again. But the catch is the length of time it takes to do that. Obviously, it takes 1 year for the Earth to go around the Sun, and it takes approximately 2 years for Mars to go around the Sun. And the blue line is somewhere in between. It takes a little less than 1.5 years for an object to follow the Hohmann transfer to Mars and back. And that's the catch. If you decide not to land on Mars and come back to the Earth orbit, it takes you a little less than 1.5 years to arrive back here. But where is the Earth now? Well, in 1.5 years, of course, the Earth will have travelled around the Sun once and a little bit less than another half. So the Earth will be approximately here. So if you follow the Hohmann transfer, you'll come back to Earth orbit, but the Earth won't be there anymore. And that's the catch with Earth-Mars transfers. The timing is such that you can't do it quickly. It takes you about 8 months to get there and about 8 months to come back again. And you can't come back immediately because the Earth won't be in the right position. Essentially, you have to spend 8 months getting there, and then if you're going to arrive at Mars, you then have to stay on Mars for a while in order for the Earth and Mars to be in the right relative positions to follow the home transfer back to Earth again. That's why Mars missions will take a couple of years or so minimum, because you really can't do it quickly. Remember, you can go to the moon and back quite happily in a couple of weeks, but to go to Mars and back is going to take you a couple of years. A rather difficult undertaking. So what about getting to other planets in the solar system? Well, back in the 1960s, it was realized that if you fly a spacecraft close to a planet, you can slingshot past it. In other words, you can do a so-called gravity assist, whereby you can rob the planet of some of its momentum and make the spacecraft go faster. The planet will end up going slower, but that will hardly notice. By using this slingshot or flyby or gravity assist, you can actually explore the outer solar system, these vast distances in the outer solar system, a lot faster without using fuel. And remember, if you don't use fuel, if you use a gravity assist, that means that your spacecraft can be lighter and you can use whatever payload you have for sending up your cameras or spectrometers or magnetometers. You can do more science if you take less fuel for a given payload. So it's always good to use whatever gravity assists are available to you. So how does a gravity assist work? If we think about an object on Earth, for instance, the object at the top of a hill, there's a hill and a valley and another hill. Let's imagine that object is effectively stationary at the top of the hill, and then we give it the slightest nudge, in which case it'll roll downhill and gain speed as it falls down the hill. It'll have a maximum speed at the bottom of the valley, and then of course it will lose speed as it climbs the hill on the other side. And if the second hill is exactly the same height as the first, it will end up back at the top of the second hill, again with zero velocity. This assumes, of course, this assumes zero air resistance and zero friction. This is an ideal situation. So in other words, whatever speed you gain on the way down, you lose on the way up. Not only that, but at any height, it doesn't matter what height you choose, if you pick a height, then the velocity of the object on the way down is exactly the same as the velocity of the object on the other side on the way up again. It doesn't actually matter what the shape of the hills and the valleys are. It doesn't matter if one hill is higher than the other. That's irrelevant. All that matters is you're trading off how much you've fallen to how much you've gained in speed. And so when you arrive back at the same height, you must have the same speed. So according to that, you will never gain anything by driving down a hill and then driving up the other side of the hill. Perhaps any cyclist already knows that. Whatever you gain on one, you'll lose on the other. So how does it work with gravity assists in space? Let's think about flying past Jupiter. So we are going to pass Jupiter. We're going to come in on the left and we're going to pass Jupiter. And of course, the closest approach to Jupiter will be the maximum flyby speed. So we're going to come in with some inward speed and we're going to leave Jupiter with some outward speed. But the question is, if you only gain on the way in and then lose it on the way out, how can you possibly win? Well, you win because the inward speed and the outward speed are relative to the speed of Jupiter. And remember, Jupiter is orbiting the Sun. Let's just imagine it's in the direction of the big yellow arrow there. So if we arrange it so that the inward speed and the outward speed are pointing in different directions, so for instance, if we come in this direction but we leave in the same direction that Jupiter is traveling, if the inward and outward speeds are the same speed relative to Jupiter, then if we leave in the direction of Jupiter, then we're gaining that extra momentum, that extra speed, because in a sense we're piggybacking on the speed of Jupiter itself. So although the speed relative to Jupiter doesn't look any different, the speed relative to the Sun can be substantially increased. For instance, an object might approach Jupiter at a speed of 10 kilometers a second, but it might leave Jupiter's influence at a speed of perhaps 25 kilometers a second relative to the Sun. And that's how gravity assists give us the boost we need. That was used in the early 70s when Pioneer 10 left the Earth, the pink here, on its way to Jupiter. You can see the pink when it reaches Jupiter. Notice the change? There's an abrupt change in direction and an abrupt change in speed. The speed is actually in the bottom left as digits, but it's a bit difficult to keep your eye on those. Let's just watch the pink again. As the pink approaches Jupiter, it flies by Jupiter, gets a gravity assist, and heads off in the direction of Jupiter at a much higher speed. High enough indeed to leave the solar system. The object has now received enough speed to reach escape velocity. And the same was true with Pioneer 11, launched a little bit later. This time it flew by Jupiter and used a gravity assist from Jupiter to head off to Saturn. Notice that Saturn wasn't in a particularly nice position, so it had to cross most of the solar system to get from where Jupiter was to where Saturn is. The little tick marks, by the way, on the purple line just indicate that the trajectory was just above the plane of the ecliptic, the plane of the solar system. So there's the kick from Jupiter. It then travels across the solar system, slightly north of the plane of Jupiter and Saturn's orbit, and then it passes Saturn and gets another kick and ends up heading off to the left there again with a speed fast enough to have Pioneer 11 leave the solar system. In the late 70s, Voyager 1 and Voyager 2 used the same trick. Voyager 1 left the Earth, got a gravity assist from Jupiter, and the principal mission for Voyager 1 was to get a close-up picture of Titan. And Titan wasn't in the right place to get a gravity assist from Saturn. So notice that the purple line just cruises past Saturn with apparently no change in velocity. Let's see that again. Voyager 1's mission was to take pictures of Jupiter and then to take pictures of Titan and anything else it could, but because it wanted pictures of Titan, it couldn't get a gravity assist from Saturn. So on it goes. But Voyager 2, which was launched at approximately the same time, was a few months behind Voyager 1. And so it already knew that Voyager 1 had completed its mission and had obtained images of Titan. So there was no need for Voyager 2 to do the same. Voyager 2 was free to get a gravity assist from Saturn. So in 77, again, it was launched and a gravity assist from Jupiter, and now a gravity assist from Saturn sent it on to Uranus, another gravity assist, and then on to Neptune. Again, notice no gravity assist from Neptune, and notice the tick marks tell us that the probe was actually sent below the plane of the ecliptic. That's because the people on this mission wanted the probe to get good views of Jupiter, Saturn, Uranus, and they wanted the best possible views of Neptune, so they flew over the North Pole, which sent the probe down below the plane of the ecliptic, and as a result it didn't get a gravity assist from Neptune itself. But still, the gravity assist from Jupiter, Saturn and Uranus meant that it could probe these four planets, the ice giants and the gas giants, over a sensible number of years. If we look at Voyager 2's speed as a function of distance, the vertical axis is speed relative to the Sun in kilometers per second, and the horizontal axis is the distance from the Sun in astronomical units, the distance from the Earth to the Sun. So there's the Earth at a distance of 1 AU, and the Voyager 2 probe left Earth at about 35-36 kilometers per second, but rapidly fell because it's leaving the influence, it's getting further away from the Sun, it's moving away from the Sun is pulling it back, and so the velocity is dropping until it reaches Jupiter, at which point it gets a kick. And then another gravity assist from Saturn and then Uranus. And notice in the case of Neptune, although it gets a gravity assist in the sense that it goes faster when it approaches Neptune, it loses all of that velocity as soon as it goes on the other side of Neptune. As soon as it leaves the influence of Neptune, it's actually traveling more slowly than when it arrived. Remember, they weren't that fussed about getting an assist from Neptune. They wanted to get the best possible views of the Neptune cloud cover, so they went over the North Pole. They didn't need a gravity assist from Neptune because they were already moving more than fast enough to leave the solar system. If we plot out the escape velocity from the solar system, that's the blue line, you can see that initially the spacecraft was going too slow to leave the solar system. But the gravity assist from the very massive Jupiter gave it a really big kick, and thereafter the red line was always above the blue line. So in other words, from Jupiter onwards, this object was always going to leave the solar system, unless they deliberately slowed it down by doing the opposite of a gravity assist and reducing the speed rather than increasing the speed of the spacecraft. So using gravity assists to cover these enormous distances between Jupiter and Saturn, Uranus, Neptune, etc., gravity assists to the outer solar system perhaps seems like a very sensible idea. But what is not so obvious is that gravity assists are also used to visit the inner planets. So for instance, Bepi Colombo in 2018 had a gravity assist by flying past the Earth and then flying past Venus and then flying past Venus for a second time, which we're going to see in just a second. There it goes. And then a gravity assist from Mercury. Why all these gravity assists? If we're falling into the inner solar system, we have plenty of speed. That's the problem. We're going too fast if we're falling in towards the sun. In this case, the planet flyby, the gravity assist, is used to lose speed in order to get to the right speed to rendezvous with Mercury. Otherwise, if we leave Earth and simply fall into Mercury's orbit, we'll be going way too fast to actually go into Mercury orbit. So a flyby can in principle accelerate or decelerate depending on the geometry. Do we end up leaving the influence of a planet in the same direction as the planet, in which case we gain speed, or in the opposite direction, in which case we lose speed? In both cases, we save fuel. We can change the velocity of the spacecraft, we can get a delta V without firing the rocket motors, without firing the engines, without using fuel. And anything that allows us to get from A to B without using fuel is a good thing. Less fuel means more science, because we can put more instruments on board if we have less fuel. Now, in some cases, we have to take fuel with us. For instance, Cassini going to Saturn, they wanted to look at not only the clouds of Saturn, they wanted to look in detail at the rings and the moons of Saturn. So having arrived at Saturn, Cassini was then told to go into various orbits. You can see here between the years 2004 and 2017, Cassini continually changed its orbit. It's a very complicated pattern. Let me just spin it so you can see it. You can see that there's a huge number of orbits because the scientists wanted Cassini to dive close to the planet or close to the rings or close to a particular moon to get the best possible vantage point for their imaging. And so they were continually changing over a period of years the orbit in which Cassini was in. But that meant that you had to take enough fuel with them in order to change their orbit. Every time you want to go from one orbit to another, if there's no objects close enough that you can do a gravity assist, you have to fire your rocket motors. And the more fuel you need, the less science you can do, and you have to, of course, build in a particular mission lifetime. If you want it to last a certain number of years, a certain number of maneuvers, you have to take a certain amount of fuel with you. So let me finish with these parking places. How can you park a spacecraft at a particular point in space? What are these Lagrange points that you might have heard about all about? So let's return to our picture of size and orbit. This is important for what comes next, so I'm going to repeat what I said earlier. The green planet is closer to the sun, so the gravitational pull is stronger, and so the planet moves fast to stay in orbit. The red planet is further from the sun, so the gravitational pull is weaker, and so the planet moves more slowly. And so clearly those 2 years are different. The green year is not the same as the red year, the length of time they take to go around the sun. And we can think of that in terms of the pull on the red, as the yellow arrow there shows that the pull from the sun on the red planet is a little bit weaker than the pull from the sun of the green planet, a slightly larger arrow there. Greater the distance, the force is less. Is that always going to be the case? Well, if we're only thinking about the pull of the sun, yes, we can't change the gravitational pull of the sun. But we can, if we're clever, arrange it so that the object in the red orbit feels an additional gravitational force. Let's assume that green is the Earth orbit. So the green dot is the Earth and the green circle is the Earth's orbit. So that's going to go round in 1 year, exactly 1 year. The red orbit, under normal circumstances, the object in the red orbit would orbit with a period of more than 1 year. But what if the red orbit is close enough to the Earth so that the red object is not only pulled towards the sun, but it's pulled towards the Earth as well? So it has to be quite close to the Earth, but what if it was pulled by the sun and the Earth? And yes, there is an orbit, as indicated by the red orbit there, which is at just the right distance so that the pull of the sun, indicated by the yellow arrow, and the pull of the Earth, indicated by the green arrow, add together such that instead of orbiting in more than a year, the red orbit is 1 year. That means that the red object would go round the sun at the same 1 year orbital period as the Earth. And so if we follow that, you notice that the red is always pulled towards the sun, and that's the same direction as pulling it towards the Earth, because they are both going round the sun in 1 year. So as seen from the, let me run that animation one more time. As seen from the Earth, the red object appears to be stationary in the sky. It's always on the opposite side of the sun. No matter what time of year we're talking about, the red object is always diametrically opposite the sun. And that's precisely what we mean by Lagrange points. If we look at the red on the right-hand side, we can see that that is what we mean by L2, Lagrange point 2. It's the point that's pulled by the sun and the Earth so that L2 goes round the sun in a year. So it effectively stays in step with the Earth. Notice that this is not to scale. I've exaggerated the orbits just to make them clear. The distance from the Earth to the sun is 1 astronomical unit, and the distance from the Earth to L2 is approximately 1% of that, approximately 0.01 astronomical units. So quite definitely not to scale. The idea for L1 is conceptually just the same. It's just that L1 is inside the orbit of the Earth. This time we can see that, as seen from L1, if we imagine an object at L1, the sun is pulling in one direction, the Earth is pulling in the other direction, and so the gravitational pull is less than you would expect just from the sun alone. And that's why the orbit of L1 around the sun isn't faster than 1 year, it's equal to 1 year. So again, L1 goes round the sun in step with the Earth. Again, the distances, not to scale in this diagram, the distance from the Earth to the sun is 1 AU, and L1 to the Earth is approximately the same distance as L2 to the Earth. It's about 1% of that. L1 is a great place to put a spacecraft that observes the sun, because if they go round lockstep, then the Earth never gets in the way of L1 observing the sun. L1 always has a direct line of sight to the sun. The Earth never gets in the way. How do we calculate Lagrange points? Well, we know what gravity is. We know from Newton that the gravitational pull between two objects is given by the mass of those two objects and the distance between them. That's all we need to know to calculate where these Lagrange points are. So all we need to do is to apply what Newton understood as the gravitational pull between two objects to calculate where do we have to be, L1 or L2, in order to go round the Earth in 1 year. And there's the maths. There we go. So big M is the mass of the sun, little m is the mass of the Earth, big R is the distance from the Earth to the sun, 1 astronomical unit, and little r is the distance we're trying to calculate. Where are the L1 and the L2 points? So all we have to do is solve that equation for r. Simple. Okay, I did say it's not that hard if you just skip the maths, so I guess we're just going to have to skip the maths, aren't we? So it can be calculated using Newton's laws for the gravitational pull between two objects, and we can calculate where these Lagrange points are. Turns out there's 5 of them. I've mentioned L1 and L2. L3 is on the other side of the sun. doesn't seem to be very useful because we can never see any object that's at L3. And L4 and L5 I'll mention in just a moment. But L2 is a useful place to put a spacecraft because, for instance, if we were to put a spacecraft there, such as this little graphic of Gaia, a sun shield on this side, notice that the sun shield blocks the light from the sun and blocks the light from the Earth and blocks the light from the moon. The sun, the Earth and the moon are all in the same direction as seen by L2. And therefore one sun shield, one shield, will stop all of the light or the heat from these objects. Whereas if you went in some other orbit around the sun, then the sun and the Earth and the moon would be in different parts of the sky and it would be very difficult to shield from those at any given time. Whereas one sun shield will do the trick if you're sitting at L2. L2 is actually in Earth's shadow, so just like the moon can cast shadows onto the Earth's shadow is somewhat longer, so it extends further into space. L2 is approximately 1 million miles away from the Earth, sitting there hovering above midnight. Remember, there's the Earth, so noon is on this side of the Earth and midnight is on this side of the Earth. So L2 is a point that's basically hovering 1 million miles above midnight. And 1 million miles is about 4 times further than the distance from the Earth to the moon, and as it happens, the Earth is about 4 times bigger than the moon. So the Earth's shadow extends approximately to L2. If you were at L2, you would probably see an annular eclipse. In other words, the sun would just peek around the outside rim of the Earth. So if you've got solar panels and you want to make sure you've got electrical power, such as the James Webb Space Telescope, for instance, you would not want to park at L2 because you would be in shadow. So Gaia and James Webb Space Telescope both orbit around L2 as indicated by this little cartoon. It's not actually sitting at the red dot, it's actually making a little so-called halo orbit around L2. A halo orbit works because if a spacecraft moves away from L2 in the sense of up or down in this particular graphic, in other words, if it moved in the direction I'm indicating with my little mouse, if it moves up, the Earth tends to pull it back down again. If it moves down, the Earth tends to pull it back up again. In other words, it's self-correcting in this direction. We can move in any direction out of the plane of this screen, and the Earth will tend to pull it back again. However, in these different directions, if an object starts to drift towards the Earth, then the Earth pulls it even more strongly. And so any object that moves away from L2 towards the Earth will continue to move towards the Earth. And indeed, if it drifts away from the Earth, it will continue to drift away from the Earth. So the behavior of an object depends on which direction it's moving. And one way of visualizing that is to use these sort of contour maps, as it were. So the ability of a spacecraft to park at a Lagrange point can be visualized if we think of these contours, think of them as being height, and think about a ball that wants to roll downhill. So the red contours are high and the blue contours are low, and we're thinking about an object that wants to roll downhill. And it helps to just blow up what we're talking about around L2 rather than keep the whole picture. Let's just blow up this region around Earth and the L2 point, red dot. Remember, the red contours are high and the blue contours are low, and we're interested in, well, if a ball wants to roll downhill, where will it roll if we place it somewhere in the vicinity of L2? Well, those arrows show you the direction of downhill. If you're here, where my cursor is, downhill takes you towards L2. And similarly, if you're up here, downhill takes you towards L2. So there's the self-correcting part of an orbit sitting around L2. However, if you move to the left towards the Earth, you'll continue rolling downhill until you hit the Earth. And if you move to the right, you'll continue rolling downhill away from the L2 point. So in other words, L2 is not a hilltop. Also, L2 is not a well. you can see that downhill depends on which direction you're talking about. So L2 is actually a so-called saddle point. Mathematicians would express it as a function as indicated there, but the rest of us would say, well, it's not a saddle point, it's a Pringle. L2 is a Pringle. The James Webb Space Telescope is orbiting around a Pringle. So the James Webb Space Telescope and Gaia are making small orbits around the L2 point, and they can orbit in this direction quite happily because it's self-correcting. When they move in one direction, the pull of the Earth tends to pull it back towards L2. But if the James Webb Space Telescope were to drift towards Earth, which it is doing continuously, then it will need a station-keeping nudge every once in a while just to push it back. In other words, the James Webb Space Telescope is orbiting just ever so slightly on the Earth side of L2, such that it slowly drifts towards the Earth, and then perhaps every 6 months or so they'll use a small amount of fuel just to nudge it back towards L2, where it will continue to orbit and it will slowly drift towards Earth, and then another 6 months later they'll give it the smallest of nudges just to push it back to L2. So it won't need much fuel, and because they were phenomenally accurate when they placed James Webb Space Telescope close to the L2 point, they didn't use much fuel to get there, which means all the fuel they have on board can be used for these station-keeping nudges, which means its mission has been extended from a nominal 5 years. It now has enough fuel perhaps to last for 10 or 15 or even more years, which is amazingly good news. So what about the other Lagrange points? Why are some asteroids found at Jupiter's L4 and L5 points? If we come back to that sort of donut and think about what's going on, well, it is possible for objects to orbit loosely around these contours. In other words, objects can hover around L4 and L5. They won't sit exactly at L4 and L5. They will tend to move around about L4 and L5. There's not much there at the L4 and L5 point of the Earth's orbit because the Earth's gravity isn't particularly strong. But for larger planets like Jupiter, then L4 and L5 have collected a few lumps of rock. The so-called Trojan asteroids are sitting there at L4 and L5, peppered around quite a large region of space. And it's not just those points which tend to collect objects. In principle, an object can travel on any of the contours indicated by that rather odd-looking donut. And some of them are really weird. For instance, if I trace one of them out, you wouldn't believe that an object can actually follow that red line. And the arrows tell you the direction that the object is travelling in. And it looks really weird, but it still obeys the basic rules. When it's closer to the sun, the green line is the distance from the Earth to the sun. So when the object is closer to the sun, it's actually travelling faster than the Earth because the gravitational pull is stronger. And if it's going round anti-clockwise, so we're looking at the Earth's orbit as seen from above, then the object is going round faster than the Earth, which means it gains on the Earth and it goes round faster. And it will eventually catch up with the Earth, at which point the Earth pulls on it, and it pulls it to a point further away from the sun. What happens when it's further away from the sun? Well, the sun's pull is less, and so it travels more slowly, which means it's now travelling more slowly than the Earth, and hence it lags behind the Earth and follows the red curve and comes all the way back again. So it looks really odd. You have to remember that this whole thing, the Earth is not static. The Earth is going around the sun, and this object is going around the sun either faster or slower than the Earth is. And these so-called horseshoe orbits might sound really weird, and you might think, well, mathematically it's possible to get an object to move like that, but surely none actually do. Well, yes, horseshoe orbits have been found, not so much in objects moving around with the Earth, but when we study, for instance, the ring system of Saturn and the moons of Saturn, we find objects that are indeed moving in horseshoe orbits. Let me finish with perhaps the weirdest orbits of all. Here's 3 objects that are static. They have been placed at these particular locations and they are not moving, and we're going to let them go and see what happens under gravity. If we assume they're all the same mass, then clearly the red object is going to be attracted to the right as it's going to be attracted to the blue and the green. The green object is going to move to the left because it's attracted to the red and the blue. And the blue is actually very slightly closer to the red. So the blue is going to move down and slightly to the left. But trying to predict what would happen when we let these three objects go is very difficult. And when we actually run a simulation, the results are far from intuitive. Let's watch them. You wouldn't really believe that that is a genuine simulation of what these objects do. Notice that they stop and then fall back along exactly the same paths again. So these are not closed objects. They are not closed loops. They are not anywhere close to being circles or ellipses, but they are still obeying the rules for two objects of given mass being attracted by the force of gravity. Is it possible for a triple star to behave this way? Well, no, because there's no way we could start the motion. There's no way we could find three objects of exactly the same mass, and there's no physical way we can start a three-star system with each of three stars born at three different positions with no relative velocity. They would bound to be moving because stars are born out of a big cloud of hydrogen which is rotating, and there will be all sorts of chaotic motion of that cloud to generate the stars. So this is a mathematical curiosity. We wouldn't expect ever to find three objects actually following open loops like this. And don't get me started on black holes, because close to a black hole, space is so phenomenally distorted, we can't rely on Newton's laws of motion to tell us how objects are going to move. We have to rely on general relativity to tell us how space is distorted, and hence how objects are going to behave around massive compact objects like neutron stars or black holes. So I've been telling you about rocket science and orbits and how we can go from one orbit to another in the solar system and use gravity assists. And I've been telling you about the parking places where we can position either spacecraft, or we can catch perhaps asteroids and have them park there. But the question remains, why is rocket science considered to be so hard? Hence the phrase, it's not rocket science. Well, absolutely. There are some objects in the solar system that move in ways which are not, at first sight, intuitive. Celestial mechanics or orbital mechanics is sometimes not the sort of thing that you can pick up and just say, yeah, I can see what's going on there. Sometimes you have to rely on physical simulations to show you what's actually happening. And indeed, calculating how to put the James Webb Space Telescope into orbit around L2 was not trivial. We might understand how to do it, but the actual mechanics, the actual precision required, especially given the phenomenal accuracy that they actually achieved, was quite amazing, allowing us to extend the life of the James Webb by using a minimal amount of fuel. So understanding the principles is one thing, calculating and actually doing it is another. But the underlying idea, the underlying concepts are simple. The underlying idea is straightforward enough. Stronger gravitational pull leads to faster motion. And you can easily remember that just by reminding yourself that the Earth goes around the Sun faster than Mars. That is pretty much all there is to it. The rest is just maths. After all, it's not rocket science. Thank you for listening.